one more factor r to come, all right? So we have this one more factor r to come. Did you wonder why we have this one extra factor? So when you change the variable, you have to add in this derivative. And this is actually the equivalence of the derivative for here, okay? So we actually use this change of variables a lot. But I want to have a general formula. So if I have a integrate double integral dx dy, so I want to rewrite it into a new pair of variables. Basically, I want to go from from xy to uv. So this is a general formula. So if I want to change the variables from xy to a new pair uv, then I need to switch between xy to uv. So these are two defining functions for x and y. And then this one extra factor is so-called Jacobian factor. So it's partial xy, partial uv, and duv. Okay? So this is a much more general formula. It will be the formula you can use when you change the variables from any old pair to a new pair. Okay? In this particular case, I changed from xy to r theta. In any general form, I changed from xy to uv, and this one extra factor coming is the so-called Jacobian factor. So this partial uv partial is so-called Jacobian. It is a determinant of 2x2 matrix. Okay. So here I have two pairs of bars, which I have to remark. This is a determinant of 2x2 matrix, right? So this determinant can still be negative. When I put two long bars here, I'm just taking the derivative. I'm just taking a determinant. When you plug in this double integral, I'm taking another absolute value. So these two pairs are separate pairs. I compute the determinant, I get a number. And then in the double integral change of variable formula, I'm again taking an absolute value. So this is nothing but a number. Okay? This is nothing but a positive number. Okay? So again, here is the determinant. So here is absolute value. So you compute 2x2 matrix. You compute the determinant. And then you take an absolute value as a number to plug in this double integral. Okay? So now, finally, I'll be able to verify in the polar coordinates why I do have to include this extra factor of r. Which means the only thing I need to compute is partial x, y, partial r, theta as a determinant. And then I take a absolute value and see whether it is indeed this extra factor r. Okay? So here is what I want to verify. So I take the Jacobian partial xy, partial r and theta. So this is nothing but an application of partial derivatives, where x is equal to r cosine theta, y is equal to r sine theta. All right? So this guy is equal to partial x, partial r, partial x, partial theta, partial y, partial r, and partial y, partial theta. In Jacobian, it is a 2x2 matrix, but also we have to remember the order. Okay? So the first row is with respect to x, second row is with respect to y. First column is with respect to r, second column is with respect to theta. Okay? So there's a particular order within this Jacobian. So let's compute it again. Partial x, partial r, what do you have? Going from integrals to derivatives, it should be a much better application, right? So it's cosine theta, x theta, minus r sine theta, partial y, partial r, sine theta, partial y, partial theta, r cosine theta. So if I compute the determinant, I'm getting an r cosine squared theta minus r sine squared theta. And amazingly, I do have an r in the end. R, as we agreed, is always non-negative. So taking the absolute value doesn't change anything. That's why I have r as the extra factor. So in the very beginning, I asked you to remember to include r. Here, we actually verify by our general formula, it is indeed the correct factor you need to add in. Okay? Questions? So I have multivariable in 2x, y. I can also do it in triple integral as well. In triple integral, I need to change my formula a little bit. So if I have dz, dv, and I'm taking the range in D, I switch it into UVW. So it's going to be T of UVW, H of UVW, and P of UVW. And then this Jacobian factor is going to be partial xyz to partial UVW, du dv dw. And the Jacobian factor is going to be a very similar form. So partial x, partial w, partial y, partial w, and then I add another rule, partial z, partial u, partial y, partial v, partial z, partial w. So it's a 3 by 3 matrix, and then I need to compute Jacobian as a determinant. In a triple integral, I take the absolute value again. Okay, so this is 3 by 3 matrix. And this has also been applied before in spherical coordinates, right? In spherical coordinates, I change it from x, y, z to rho, phi, and theta. And this factor is, what is the factor here? Rho square sine phi. You should really make a tattoo out of it. You cannot really forget that. This rho square sine phi is a factor you should not forget, at least within this semester. I also want to verify that. Okay? But this is going to be a much more complicated task, as you can imagine. I have 3 factors, and I have a 3 by 3 matrix. Okay? But I do want to recall the formula we had before. So x is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. And z is equal to rho cosine phi. All right? Yes? You're going to have to remember this. Okay? If you're not good at trigonometry, you have to remember this formula. If you're really good at trigonometry, you draw x, y, z space, and then you find an array, identify rho, identify phi, identify theta. You can use trigonometry to simply derive these formulas. Okay? Or, if you're not good at trigonometry, use this spherical coordinate system to practice your trigonometry skills. Okay? And then I want to compute partial x, y, z to partial rho phi theta. So I don't take the absolute value here, so let's worry about the absolute value in the end, which is equal to partial x, partial rho, partial x, partial phi, partial x, partial theta, partial y, partial rho, partial y, partial phi, partial y, partial theta, and in the end, partial z, partial rho, partial z, partial phi, partial z, partial theta. Okay? And then it's just 3 equations. I need to take derivatives repeatedly. Partial x, partial rho, you can actually do it by yourself. Okay? So 3 simple equations and take the derivatives for 9 times. So partial x, partial rho, I'm getting a sine phi cosine theta. Partial x, partial phi, I'm getting a rho cosine phi cosine theta. partial x, partial theta, I'm getting a minus rho sine phi sine theta. So partial y, partial rho, I'm getting a sine phi sine theta. Partial y, partial phi, I'm getting a rho cosine phi sine theta. And partial y, partial theta, I'm getting a rho sine phi cosine theta. Partial z, partial rho, I'm getting a cosine phi. Partial z, partial phi, I'm getting a minus rho sine phi. And partial z, partial theta, I'm getting a 0. Okay, so this is a 3 by 3 matrix. I need to take the determinant of. Have you learned about how to take the determinant of 3 by 3 matrix before? Some of you have, some of you probably not. But in any case, we have done a little bit of this when we do the cross product. Okay? So you cannot yank me anymore. So in cross product, we did see 3 by 3 matrix, and in that case, we did compute the determinant. Okay? But in that case, it's a little bit easier. I have I, j, k here, so I'm expanding the 3 by 3 matrix by the first row. In here, it's actually easier to expand the 3 by 3 matrix by the third row because you have a 0 here. Okay? You can expand the matrix by any row. Here, I don't want to spend too much time to talk about how to compute the determinant of a 3 by 3 matrix. The only thing I'm saying here is I want to expand with respect to the third row. So I have cosine phi right here. So cosine phi, then multiply by the 2 by 2 matrix when I delete this row and this column and this row. Okay? So I can delete this column and this row. I'm getting a 2 by 2 matrix. It's going to be rho square. So cosine phi sine phi cosine square theta. Cosine square theta. Minus, I got a plus rho square sine phi cosine phi cosine square theta. I have sine square theta. I have sine square plus cosine. I'm super happy. And also, I need to worry about the prefactor here. This is the this is the third row, first column. So this is a good one. I don't have to multiply by -1 here. So in the second thing, I have to expand with respect to this factor. So I'm deleting this row and this column. I'm getting a 2 by 2 matrix with respect to these 4 entries. And then I'm computing the determinant of that. But this is the third row, second column. That's why I have to have a -1 in front. So -1 multiplied by minus rho sine phi, and then multiply by the determinant, which is rho sine square phi cosine square phi. Minus, I got a plus rho square, rho sine square phi sine square theta. Okay? So in the end, here I'm adding these two factors, which means I'm getting a rho square sine cosine square phi sine phi. I have cosine square plus sine square, so I don't have anything here. Okay? So in here, I'm getting a plus rho square. I have a sine, so it's going to be sine squared, then sine cubed. Sine cubed phi multiplied by cosine square theta plus sine square theta. So I'm getting a 1 in the end. And then I can combine the like terms here. The like terms are rho square and then sine phi. And then I need to multiply by cosine square plus sine square, which I'm again very happy. So I'm getting a sine square, rho square and sine phi in the end, which is exactly the factor we need to add in. Okay? Okay, so in the class, I already demonstrated how to compute the Jacobian factor in the most complicated form. So on online questions, all the problems are easier than this one. So you have no excuse of saying this is too complicated. Okay? So In the online homework questions, you will be able to ask to compute the Jacobian when you change from one triple of variables to the other triple of variables. What you have to do is still taking 3 by 3 matrix, computing 9 different types of derivatives, and then compute the determinant of Jacobian. But in the end, remember to take the absolute value. Okay? In it, remember to take the absolute value. So we have verified both cases. Okay, so in the end, I will give you a much easier question to practice. So I want to compute. Where R is bounded by y minus x is equal to 1, y minus x is equal to 4, y plus 2x is equal to 0, and y plus 2x is equal to 4. Okay. So first of all, this is the double integral. All right, this is nothing but a double integral. And then I need to identify where this region is. This region is bounded by 4 different lines. All right? They're bounded by 4 straight lines. They're all linear functions, so they're all straight lines. Are you with me? They're all straight lines. So in fact, I can try to find where this region is. Try to find these regions, and then identify it as either x simple or y simple or polar or r simple, or if it is a cube, that's the best case. Okay? I can try to graph this term. So y minus x is equal to 1, so y is equal to x plus 1. So it's going to be 0, 1. This is the line. And this is y is equal to x plus 4, so it's 1, 2, 3, 4, so this is the line. So y is equal to minus 2x, so it's going to be minus 2x right here. And then this is a minus 2x plus 4, so this is going to be this is the 1, 4. Yeah, this is going to be the 1. Okay? So this is y minus x is equal to 1, y minus x is equal to 4.